The 6.8 volt Zener diode in the circuit on your screen is specified to have Vz is equal to 6.8 volts at Iz equals 5 milliampere, Rz equals 20 ohms and Izk equals 0.2 milliamperes. The supply voltage V plus is nominally 10 volts but can vary by plus minus 1 volts. Now this is what you have to do. Part A, find V0 with no load and V positive at its nominal value. Part B, again with no load, find change in V0 from a plus minus 1 volt change in V plus. Specifically find delta V0 over delta V plus, known as line regulation. Part C, find load regulation delta V0 divided by delta IL for IL equals 1 milliampere. Remember, IL is the load current. Part D, find the change in V0 when RL equals 2 kilo ohms. In other words, when a load of 2 kilo ohms is connected across the Zener diode. Part E, find V0 when RL equals 0.5 kilo ohms, and part F is find minimum value of RL for which diode is still in breakdown region. Seems hectic? Don't worry, we are going to do them together. First, we write down all the known quantities at the top of our paper. We see what is missing, and that is Vz0. And so using this equation, we find Vz0 to be 6.7 volts. Let us incorporate the Zener diode model in this circuit. With no load connected, the current through the Zener diode is given by Iz equals to I, the current from the source, equals V positive minus Vz0 divided by R plus Rz. This is simple Kirchhoff's voltage law. Iz comes out to be 6.35 milliamperes. So we can easily calculate V0, and it comes out as 6.83 volts. And this is what we were asked. For part B, to find the result on the output from a plus minus 1 volt change in V positive, we can employ a voltage divider. When we put our values, the answer comes out to be plus minus 38.5 millivolts. However, we were asked a line regulation which is 38.5 millivolts per volts. In part C, we incorporate the load resistance with our circuit. We notice that when a load resistance draws a current of 1 milliampere, the Zener current will decrease also by 1 milliampere. Therefore, the change in voltage can be given by delta V0 equals Rz delta Iz, and when we put in the values, the change in V0 comes out to be minus 20 millivolts. Our load regulation is hence minus 20 millivolts per milliampere. Now you might wonder, how did we get this delta IL? Remember that without a load, IL was 0 milliampere, and after we placed RL, the IL value changed to 1 milliampere. That is why change in IL is a positive 1 milliampere. For part D, let's first calculate the current from the supply, that is capital I. This gives a value of 6.349 milliamperes. Notice that Rz and RL are in parallel. Now applying Kirchhoff's current law at this point, we can write a current equation as I equals IL plus Iz. Writing these in terms of the voltages, we get this expression. Solving for V0, we get V0 equals 6.759 volts. Now we need to find the change in V0. This is given by 6.759 minus 6.83 is approximately minus 70 millivolts. This is our answer. For part E, let's first find IL. This comes out to be 13.6 milliamperes. However, this is not possible because the current I supplied through R is only 6.4 milliamperes, which we calculated in the first part. The logical conclusion is that the Zener must be cut off. If this is indeed the case, then V0 is determined by the voltage divider formed by RL and R, and that is 5 volts. Since this voltage is lower than the breakdown voltage of the Zener, the diode is no longer operating in the breakdown region as we had just proposed. Now for part F, for the Zener to be at the edge of the breakdown region, IZ needs to equal IZK. This gives IZ equals 0.2 milliampere and VZ also needs to be equal to VZK, which gives VZ equals 6.7 volts. Now how did we get this value? Let's come back to this graph and we can see that VZ0 and VZK are almost equal values. Therefore, when we know the value of VZ0, we can also find the value of VZK. Now at this point, the lowest or the worst case current supplied through R is 4.6 milliamperes. We choose 9 because V positive has a positive and negative variation of 1 volts. And so the load current will be 4.4 milliampere. Again we use Kirchhoff's current law on this node. Finally, the corresponding value of RL is approximately equal to 1.5 kilo ohms. You are urged to complete this entire exercise on your own. However, let us show you part E on a software called Multisim. Multisim is a software by National Instruments NI. We are going to use this software and recreate our solution. So let us first learn how to draw it. We go to this one, Place, and we click on Components. Now we first need a DC voltage source. So we click on this, Power Sources, then we go to DC Power. Click OK and we place it. Next we need a resistor. Go in Basic. Click on Resistor. Place it here. Now we need another resistor for the load. We again click on OK. Place it here. We are just placing the components. We are not arranging them in the circuit yet. Now, what else do we need? We need a Zener diode. Remember in our question we had a 6.8 volt Zener diode with an IZ of 5 milliamperes. Let's use Google to find our appropriate diode. Here we are. Now this shows plenty of models. We have 1N4736A, another one. We have 1N5235B. Let's just choose one of them and we choose 1N5235B. Going back to Multisim, we search for it. We write its model. Here we have it. Now we need to make our circuit. Close it. Watch carefully what I do. We rotate this resistor via Control R and we bring it in line. Now we place wires. We also place the ground. What else do we need? We need to change the values. This is 10 volts. This is 500 ohms or 0.5 kilo ohms. This is 2K. And that's it. But how are we going to measure that? For that we need a voltmeter. We go to indicators and here we have the voltmeter. Place it here, and as you know with voltmeters they need to be placed in parallel with the output. Now we are ready to calculate and we simply click on run. And we have this value here, 6.744, which is not so different from the one we calculated, which was 6.7593. This was just to demonstrate how to begin using this software. We are going to be using this extensively in future modules and courses. If you don't have it, you can also use Spice as an alternative, but I urge you to purchase this and use it in this course.